is Connor Casso, and I am the lead for experiment 2, or experiment 1, which is the clay piron experiment. So some goals for the experiment. The experiment is heavily emphasized on thermodynamics, so we want to determine the latent heat of vaporization using the clay piron equation, and then verify our results using the steam tables. Also, we want to gain an understanding of how thermodynamic properties cannot be measured. Thermodynamic properties that cannot be measured can still be found using measured properties, which is a big aspect that we see in thermodynamics. So some background to the experiment. The clay piron experiment is aimed to investigate the relationship between the pressure, volume, and temperature of a gas during a change of state, specifically during a phase change. So the phase change taking place in our experiment will be from a liquid to a liquid vapor mix. The clay piron experiment was also a crucial contribution to the development of thermodynamics as from a scientific standpoint, and continues to be an important part of the study of phase transitions. So the clay piron equation is actually derived from the ideal gas law, which can lead to some irregularities in our data. So the clay piron equation relates the slope of the phase boundary between two phases to the difference in the enthalpies and specific volumes. Specifically, we'll be analyzing how a property that cannot be measured, such as enthalpy, can be directly found by the measurement of pressure and temperature. So here we have two derived equations, one specifically derived from the ideal gas law. We have saturation pressure, saturation temperature, latent heat of vaporization, and specific volume. So our experimental apparatus, there's quite a number of things that go into our apparatus. We start off with the flask, the hot plate, the vacuum, which plays a role in our experiment, the vacuum control valve, the centrifugal pump, the water reservoir, and our DAC system that will collect the data, as well as the thermocouple and the rubber stopper on top of the flask. Also not noted in the experimental apparatus is the boiling beads at the bottom of the flask. The boiling beads are important in our experiment because they increase the surface area of the liquid. They can also help reduce the time required for the liquid to come to a boil and to maintain a steady boil, so that it doesn't violently boil or doesn't come to a rolling boil, so that it could come out of the boil out of the flask and burn us. So the addition of boiling beads to the beaker or flask can improve the safety and efficiency of the boiling process, making it easier to heat without boiling over. So the procedure, we want to start off by turning on the vacuum pump and then turning on the hot plate to bring the water to a boil. After turning on the hot plate, we want to insert the thermocouple, which is also we also insert the tube for the vacuum, and we insert the rubber stopper as well. Once we insert the stopper and turn on the hot plate, we want to begin logging data till the water comes to a boil. Typically, this takes between 5 to 15 minutes, closer to 15 minutes on average. And then throughout the duration of the time to boil, we want to slowly close the vacuum line. And then after the water reaches a rolling boil at atmospheric pressure, we want to stop taking the data. Important note of safety is we don't want to touch the hot plate or the beaker at any point because it is boiling, so we would be at risk to burning our hands. So I took some random data points of pressure and temperature and I found the enthalpies. So I took the local derivative, which is subtracting P2 from P1 and then T2 from T1, and I found that the enthalpies found aren't actually anywhere close to the values found in the steam tables, which could be due to a variety of different reasons, such as the vacuum created and that our system shouldn't actually be based on the ideal gas law. So some uncertainties in our experiment could be the sealing on the beaker causing a pressure differentiation and temperature uncertainty in the thermocouple. Depending on how far the thermocouple is inserted, it could be too close to the hot plate. And then we're dealing with a liquid vapor mix, so the ideal gas law does not completely apply.